Hi, this is our video for Chapter 4. It's going to cover sections 4.4, 4.5, 4.8, and then one extra topic that is not in the chapter but we need to cover. We are starting with 4.4 with just a couple definitions. So there's 4 words in blue on this slide. One of them we've talked about before, right here, aqueous. Aqueous is the word we use to describe when a solution is water-based. So it just means that something is dissolved in water. The word solution is just another word for a homogeneous mixture. So remember, mixture is more than one thing combined. Homogeneous means that they're evenly mixed. So another word for that is a solution. A solution is made up of 2 parts, a solute and a solvent. The solute is what gets dissolved, so it often changes state, solid to aqueous, for example. And the solvent keeps its state, so it's the one that does the dissolving. Now, if they're already both in the same state, like mixing 2 liquids together, then the solute is the one that's the smaller amount. When we make a solution, the components will stay the same, but the quantities can vary. For example, we can have sodium hydroxide in a whole bunch of different concentrations. So when we describe a solution, we have to say not just what's in it, but how much is in it. And we can do that qualitatively or quantitatively. So we're going to talk about the qualitative descriptions in the video, and then in lecture we'll talk about the quantitative descriptions. So for qualitative, we have 2 words, dilute and concentrated. Independently, they don't mean a whole lot. They usually only mean something if we're using them to compare. Concentrated means that there's a large amount of solute. Dilute means that there's a small amount of solute. Now, what small and large means doesn't really have a whole lot of meaning, which is why I say that they have meaning if we compare them. So over here we can say that this one is the more concentrated and this one's the more dilute. Individually, we can't use those words to describe them, but in comparison we can. In section 4.5, we're looking at why a solute would dissolve, or when it will dissolve. So there's 3 attractions that are going on within any solution. There's the attraction that's holding the solute particles together. So the example down here is sodium chloride in water. So the attraction is between our cation and our anion. Number 2 is the attraction that's holding the solvent together. So water has partial charges, meaning that part of it is a little bit positive, part of it's a little bit negative, and so that means that there's going to be an attraction from one water molecule to the other. So that's our solvent attraction. And then the attraction that's going to cause something to dissolve is this last arrow right here, the solvent solute. So this is the attraction between our solute particle and our solvent. So notice that the part that's marked negative on our water, the oxygen, is attracted to that positive cation, and the part that's marked positive, the hydrogens, is attracted to that negative chlorine. Now, not everything dissolves. How we can predict or decide if something will dissolve is based on these attractions. If this attraction, that solute-solvent attraction, is the strongest, then our solute will dissolve. If the other attractions, for instance, this solute-solute attraction is the strongest, then the solute will stick together and it will not dissolve. An easy way to predict this is based on the charges. The bigger these charges are, the bigger the attraction. So an aluminum 3+ with a sulfate 2-, that's going to be a really strong attraction, whereas our sodium 1+ and our chlorine 1- is a very weak attraction. This again is showing us that same picture. So our water molecules have to separate, our cation and anions have to separate, and then as a result we can have our water surrounding our ions. And again, notice that the oxygen is surrounding the cations and the hydrogens are surrounding the anions. When something dissolves in water, we, again, like to give it labels, and the two labels here are electrolyte and non-electrolyte. This is definitely a word we hear outside of chemistry. It's a word that's used to describe Gatorade and Powerade and drinks like that. All electrolytes are ions that have been dissolved in water. So for something like Gatorade, it has salt and potassium and calcium. It has ions that your body need in it, and they use the word electrolyte just to say that they're in there. Non-electrolyte is when things dissolve in water, but they do not have a charge. They don't conduct electricity. So we can usually break these up into ionic compounds and molecular compounds. So here we've added a category. We have strong electrolytes, weak electrolytes, and non-electrolytes down here at the bottom. Strong electrolytes are ionic compounds and strong acids. They're going to completely break apart into their ions and conduct electricity very well. Non-electrolytes are molecular compounds that do not break apart into ions. So the example down here is sugar. If you drop a sugar cube into your coffee, you don't see it anymore because the individual molecules break apart, but there's no ions that are forming. So we separate the molecules, but we're not creating ions. So there's no electricity. Weak electrolytes are in the middle. This category includes weak acids, and how we describe it is that some of the molecules break apart. So acetic acid's a weak acid. Here it is in molecule form, and then some of them have broken apart to give us hydrogen cations and acetate anions. So here's our question. We're going to classify each of these as either a strong electrolyte or a non-electrolyte. So essentially we're using the same pattern we did when we were naming compounds. We're going to look at that first element, and it starts with magnesium, which is a metal. Therefore this is an ionic compound, which tells us that it's going to be a strong electrolyte. This structure starts with carbon. Carbon is a nonmetal, therefore this is a molecular compound, therefore it's a non-electrolyte. Sodium, metal, ionic compound, strong electrolyte. And last, potassium is a metal, and it's also a base, so it's an ionic compound, strong electrolyte. So we're just categorizing these as ionic or molecular, and then we can also break those into acids and bases, and that will tell us electrolyte or non-electrolyte. Within our acid categories, we do have the strong and the weak. So I did mention those on the last couple slides. Strong acids are going to completely break apart into their ions. When we write out their equation, we write it with a forward arrow only. Weak acids break apart into ions, but those ions can recombine to form the molecule, so we draw it with a reversible arrow to show that the reaction can go backwards and forwards. Now there's two words that are very similar in definition, but how they get to that point is different. So the two words are up here, dissociation and ionization. They both mean that we're going to end up with ions in solution. How we get to those ions, though, is what separates the words. Dissociation is the word we use for ionic compounds, and it means that they're going to break apart into their ions on their own. Ionization is the word that we use for acids, because acids are molecular compounds, so technically they don't have ions. The water has to pull them apart to ionize them and create those ions. So dissociation, ions are formed automatically from an ionic compound. Ionization, ions are formed through water with acidic compounds. Now, I said earlier that not everything is going to dissolve in water. The two words that we use for this: soluble if it dissolves, insoluble if it does not. In order to decide if something's going to be soluble or insoluble, we either need to do experiments or we use data from previously done experiments. This is our table of data. So it's technically two tables stacked on top of each other. The one on the top is labeled compounds containing the following ions are generally soluble. So if we see these ions, our compound is most likely soluble, and then here's the exceptions. The bottom half, compounds containing the following ions are generally insoluble. Here's our insoluble ions, and again, here's the exceptions. So we're going to practice using this table. Determine whether each compound is soluble or insoluble. So here's our table. So what we do is we look at our compound and we look for these ions. We do not need to find both of them. We only need to find one of them, and we want to find it in the first column here on the left-hand side. So we find iodine, and iodine is in the area that's labeled soluble. We check the exceptions, and silver is over there as an exception. So when iodine and silver are paired up, it's going to be an insoluble compound. Copper 2 phosphate. Again, we look for copper or phosphate. Here's phosphate. We check the exceptions. Copper is not over there, so that means that compounds that contain phosphate are insoluble. And then our last one, potassium phosphate. So we already know where potassium is at. Potassium is insoluble. We check our exceptions. Potassium is one of the exceptions, so that tells us that it is a soluble compound. Now we could have done this one also by looking up here. Potassium is soluble, and there's no exceptions. Completely acceptable way to do it. Both will get you to the same answer. Both are correct. One more acid thing we need to talk about is a couple words here. One of them is hydronium. When hydrogen forms from an acid, we get this H+, it's going to combine with water to make H3O+, which is hydronium. And then a couple other words, polyprotic and diprotic. This is referring to how many hydrogens are at the front of an acid. So H2SO4 is diprotic because it contains two hydrogens. Phosphoric acid, H3PO4, would be triprotic, and then both of those would fit into the polyprotic category, which is just kind of a generic one. Now the overall title of this slide, the Arrhenius definition, we're looking at acids and bases based off of this specific definition. When you take Chem 1B, you will add to this definition. But for this, the definition of an acid is that it's something that produces a hydrogen. A base is something that produces an OH. And here's our picture of this. Here's our acid, and we know it's an acid because it starts with hydrogen. Here's our base. We know it's a base because it ends in OH, or hydroxide. When they combine, the sodium goes with the chlorine, the hydrogen goes with the hydroxide. We make sodium chloride, and we make water. And we'll talk about more about the actual acid-base reactions during lecture. These are just some common acids and bases. It's specifically showing us the strong and the weak ones. So the strong ones are in black, and then there's a couple weak ones listed here that are listed in pink, but just kind of an informational thing. And then our last topic here is not actually in the chapter, but it is something that we need to cover. We have 4 types of reactions based on how the elements recombine. So a synthesis reaction is when we take 2 or more elements and combine them together to make one product. Decomposition is the opposite. We're going to take one product and it's going to break apart to give us 2 or more. I think I said that backwards. We're going to start with one reactant. It's going to break apart to give us 2 or more products. So here's our synthesis. We have CO and O2 combining to make CO2. Here's a decomposition, starting with iron chloride. Iron 3 chloride is going to break apart to give us iron 2 chloride and chlorine gas. And then in the displacement category, this one is just labeled as displacement. Sometimes it's also called single displacement. We have a singular element reacting with a compound, and the cation is going to switch place with that lone element. And then in double displacement, we have two compounds, and the cations are switching places. So here's our single displacement, zinc with HCl. The hydrogen and the zinc swap spots. And then down here we have also a single displacement example, iron 3 oxide with aluminum, the aluminum and the iron switch spots. In class we will talk about precipitation reactions, gas evolution, and acid base, and those all fit into this double displacement category. For these on the test, if you were given one of these types of reactions, you would have to tell me what category it fits into, but you would not have to predict the products. That's not something that we do yet. Alright, that is it for Chapter 4. Thank you.